All right. Hey guys, so welcome back to another video. Today I'm going to be talking about the area between curves. And so I want us to think back to way back when we first started working out with definite integrals, right? So when we were first working out with definite integrals, what we decided was the integral adds is an adding machine. We're adding infinitely thin slices between each curve. Like we're adding an infinite amount of Riemann sums, right? So that's what the definite integral is. Now let's think about it in terms of the area between curves, right? So given a graph of two functions, right? So I'll make one of them red and then another one blue, right? So let's say that I wanted to find the area between these two curves, right? We'll call this A and this B. So I want to find that area between those two curves, right? I know that anytime I want to do area, that's going to be a definite integral, right? So I know I'm going to be taking the definite integral from A to B. Then we'll call these curves. This one will be f of x, and this one will be g of x, right? And so if I want to take the area between these curves, I'm going to kind of apply the same thing. I want to take infinitely thin cross sections of this 2D curve, right? And what I mean by a cross section is literally just the section from one curve to another, right? So when we think about that, what we're doing is we're basically taking a slice, right? We're going to take this slice of the curve right there, right? That slice has area, right? What we're looking at is essentially a rectangle, right? So this is actually a rectangle, right? So the length of the rectangle, right? So this side of the rectangle, that's going to be the top minus the bottom, right? Well, what's the top? The top is given by this blue curve, right? That's f of x. So we know that the top minus the bottom will give us the length of that rectangle. So what that means is we have this height is going to be equal to f of x minus g of x, right? And so now we have to consider, okay, well, that kind of gives me the height, but what about this piece right here, that width, right? So this is where we're going to talk about the idea of being infinitely thin, right? So basically, here I have there's actual width to the rectangle, right? In my drawing, there's width to the rectangle. But since I'm only taking like a slice, my width is so small that we barely even consider it, right? And we can do that in math. So basically what we're doing is we're going to take Riemann sums, right? We're just going to keep adding on all of these slices, right? And we're going to keep adding slices until we get closer and closer to our endpoints, right? And so that's why we're using a definite integral, right? The definite integral will add all of these slices up, starting from A all the way up to B, right? We're going to add up infinitely many slices, right? And so we kind of denote those infinitely many slices with that dx at the end, right? So here, right, if we think about it in terms of Riemann sums, right, what is the Riemann sum? The Riemann sum is the area of rectangles, right? We know based on this rectangle right here, we know that all these slices are going to have a height of f of x minus g of x, right? To consider the fact that we're going to be having infinitely thin slices, and we're going to have a bunch of infinitely thin slices, that's what we're going to cap it off with our dx, right? So this is kind of how we visualize and understand the area between curves, right? So this is how we get this formula, right? So that's it for me today. I hope you guys learned something. I hope you guys kind of keep this mental image of the area between curves in your head, because it'll come back in a more like 3D way, I guess. So yeah, hope you learned something. Thank you for watching.